Hi, my name is Gabriel Ferreira. I am a PhD student at the University of Brasilia, or UNB for short. I'm also the new CMake build system maintainer of ns-3. And among my contributions, there is the profiling chapter that is part of the ns-3 manual. And this talk presents some of the background information for that specific chapter about memory bugs and performance bottlenecks and how to find and fix them. This presentation is split into two sections, being the first one about memory bugs and the second one about performance bottlenecks. I want to start by showing this graph produced by Microsoft Security Research, which shows the root causes of the reported security vulnerabilities grouped by class. As it can be seen from the image here, between 60 to 70% of all vulnerabilities are caused by memory bugs. These bugs can happen due to incorrect use or management of memory, which typically occurs in manually managed programming languages such as C and C++. The current slide has a few examples of the different memory bug classes. The first one is uninitialized use of memory. In this case here, the variable is never initialized, so it may contain trash from a previous process. So if the previous process have written to the same address of a value of 1, the value of a will be 1, even though it's a different process and completely different code. In the second example, we have a heap out of bounds, where we allocate a single integer, but we try to access the second integer, which will cause the out-of-bound access, where we can read or modify a variable that was not allocated. In the third example, we have use after free and a memory leak. In this case here, we allocate a single integer pointer, another integer, and then we copy the pointer of B to pointer of A, which means the original integer pointed by pointer A was lost. So we have a memory leak. And here the value of the pointer A, which is pointing to the same value as pointer B, is being freed, and now we are trying to access it, resulting in the use after free, which is also a problem because you can have a dangling pointer, in this case, pointing to a memory address that was already allocated for a different object and will be rewritten or wrongly read from. And the fourth example here is the type confusion, where we have, for example, two floats, which are two 32-bit objects or variables, and we have a pointer to a double, which is 64-bit or 80-bit on Intel, and we have this cached from the pointer to the pointer A, and when we try to print as a float, we will get the first result, and when we try to print as a double, we will get a mashup together version of those two, because they are right next to each other in memory, and they are read by this call as a single double value. Next, we have an example of heap corruption. Here we are allocating a pointer to an integer, and then we are copying 10 integers to this vector of a single integer that we will end up overwriting the equivalent of 9 integers that may have all sorts of structures in memory on the heap, which can cause the program to fail or produce bogus results. And the last example is the stack corruption, where we have a bugged function here that is properly named, and when we call this function, it will allocate two variables, a and b. It will copy the address of this function that was never called, and we'll copy that to b, And then we'll copy the value of b to the value of a minus 2, which is an out-of-bound access. But the address of a, here's the a, minus 2 means that it is modifying the address of the return address of the callee, which was supposed to be used to return to the caller. So when it hits the return of this function, instead of going to the next instruction after the call, it is going to be redirected to this other function that was never supposed to be called. So this is how shell code injection works and how attackers can take control of your program. To conclude, and why you should care about memory-related bugs is because they are really hard to find, they can easily crash your program, as seen from stack corruption, they can let your program continue while producing both results, and producing wrong results or wasting your time is really bad. So how can we find those bugs in a huge code base? And the answer is using a tool such as Valgrind on Linux, Leaks on macOS, or sanitizers, which are cross-platform and distributed with the compilers. After running your program with one of these tools, it will produce a report indicating where possible bugs were found, and you can check each one of them and fix them. And it's also recommended to use coverage tests to expose additional bugs that only happen in very specific conditions. The first case I wanted to show you was one of the out-of-bounds error we found in LTEMC, which was when the program tried to access the index -1 of the matrix of integers, which corresponds to the transport block size table variable. And when we try to access this -1 table, here in this transport block size table variable, we end up hitting the adjacent memory of MCS to ITBS UL. This is also shown with this shadow bytes representation here, where when you have 0, 0, 0, 0, zeros, we have an object in memory. And when you have kind of a buffer, which is added by the sanitizers, which are meant to be corrupted by exactly this kind of bug. And we have the other memory of the real object here. And when we try to access the wrong index, we hit this victim buffer, and the sanitizers can identify the source of the problem, which is also shown as this stack trace, which we can trace exactly what happened to expose this kind of bug, which ended up being in this scheduler. By tracing back the stack provided by sanitizers, we can find the source of the issue. So the address that we are trying to access with the wrong index was this one, where -1 ends up reading the value of MCL to ITBS UL. And this can only happen when we have NPRB equals to 0, which was not supposed to happen. And by looking even further back on the trace, we need to check who calls get DLTB size from MCS, which provides that NPRB value. By tracing back from LTEMC, we find a specific code from one of the LTE resource schedulers. And by inspecting the code, we can see that the original code did include that statement, which prevents the scheduler from trying to allocate 0 resource blocks for NUE. And by simply adding this statement, we prevent the NPRB equals to 0, which ended up being subtracted from 1 and producing the -1 index that caused the out-of-bounds error. A different kind of issue that the sanitizers can find are memory leaks. In this specific case, we found a memory leak in the main propagation loss example, which was caused by the Jake's propagation loss model and Jake's process. By using the stack provided by Leak Sanitizer and inspecting the code, we can see the reference count for Jake propagation loss model is always bigger than 0, which happened because when the Jake's process was not initialized, it created a copy of the Jake propagation loss model, which increased the reference counting to 3. And this copy was added to a mpropagation cache variable, which was kept until the Jake's process was destroyed. But it was only destroyed when Jake's propagation loss model was destroyed too. So it ended up never being destroyed. One of the possible fixes we have is unreferencing this pointer, which makes the ref count goes to, in this case, it was 3. It will end up going back to 2. And in the colors, it will end up being differencing 2 times again, reaching 0 and being destroyed successfully, not leaking any memory. And now we'll switch from memory bugs to performance bottlenecks. What are performance bottlenecks? Limitations in hardware and software that slow down the ideal performance a program could have for a combination of hardware and software. Some of those things that could limit the performance of the hardware are the CPU IPC, or instructions per clock, the clock itself, the CPU cache sizes, the CPU branch predictor, the number of execution units in the processor, which will depend which kind of instruction you are trying to run, how many loads and stores it can make per cycle, and a bunch of other stuff that can change due to microarchitectures. Another hardware characteristic that can limit the performance of our programs is the memory subsystem, which can be characterized by the bandwidth, latency, and size. And the memory subsystem is composed of multiple tiers. In this case here, we have the L1 cache, L2 cache, shared L3 cache, and the main local memory. And the closer we get to the processor core, we have higher bandwidth and lower latency. So we want our programs to maximize as much as possible the L2 and the L1 and L2 cache hits, not to fall back to much slower L3 and main memory access. Another source of overhead for our programs that can limit their performance is the operating system calls, or syscalls overhead, which is the amount of time the operating system needs to answer any call made from the program to it. For example, to open a file, read a file, close a file, update a file, open a socket, send a message, or stuff like that. And the storage bandwidth and latency, which depend not only on the physical media where the data is stored, but also in the device drivers that are available for the operating system. And why should you care about performance bottlenecks? Because they limit the scale of the simulations or any other program you are trying to run. It wastes time and money, and because bottlenecks are generally easy to find and fix. So it's a waste not trying to fix them. But how do we find these performance bottlenecks? Well, much like the memory bugs, we have tools to help locate and diagnose which kind of bottleneck we have. We have different tools for general profiling based on different operating systems, where we have perf and hotspot for Linux, Windows Performance Recorder, and Windows Performance Analyzer for Windows. We have different tools for different processor manufacturers, such as AMD Microprof, UProf, I don't know what they called it, and Intel VTune, which is pretty famous. For system calls in Windows, we have Procmon, in Linux we can use S-trace. I think macOS also have S-trace or D-trace, which are kind of similar. For memory allocations, we can use HeapTrack or mymalloc, which is a custom memory allocator, but can track a ton of interesting information about the memory allocations. I also suggest using the graphics user interface provided by those profilers to visualize and identify the bottlenecks. Intervtune is pretty special in that regard for providing this pipe visualization, which is pretty awesome, where you can see the part of the instructions in green are being retired or completed. So for every 100 instructions you send to the processor, only 30% of them are being completed. In this case, in this other case, it's 37%. In this case, we are losing 64% of the instructions due to bad speculation. These numbers are pretty weird. If you count them, you are going to see that they don't quite match 100% because this is a instruction, a function that hasn't been profiled enough times. It doesn't have enough samples to provide a clear image of this function. But I wanted to show this bad speculation part. And in this other case, we have about 60% of the instructions being lost due to front-bound issues. So front-end latency due to instruction cache misses. So the execution units are waiting for instructions to be executed. The translation look-aside buffer has a huge overhead in this case because it is not mapping the data quite as good as it could. There's a ton of unknown branches, probably the callbacks that we use in the simulator. And there is also the front-end bandwidth problems that are associated with other units. A different kind of visualization that is very common is the flame graphs, shown here below, where you have the time or any other metric you are trying to measure organized by function and the stack in it where it was called. The first case I wanted to show you about performance bottlenecks is the Spectrum Wi-Fi Fi Start RX, which was causing some tests to run for over 12 hours. And I started looking into it, and what we found was the following. So what we found is that StartRx was creating a filter, was filtering a subband of the complete channel, and then calculating the power of each subband that was processed later, which is pretty much in line with signal processing programming, but not completely necessary for us that are using that in a simulator. The solution to the problem was replacing the full channel filtering and assuming that we have uniformly sized subbands, which allowed us to save a ton of multiplications. So the code changed from filtering by zeroing out every single value that is not of interest, which means every other subband that is not the one you want to calculate the power, you are going to zero out. In this case, we just read the values of the subbands of interest instead of trying to read everything. By assuming we have uniformly sized subbands, we can also cut away the multiplication for the subband bandwidth and replacing that with a single multiplication, which made this code a lot faster than the original. These are the flame graph plotted results of the program mentioned before. And by looking at the total number of cycles spent in Spectrum Wi-Fi Fi, we had a reduction from 76% down to 25% of total cycles of the program, representing a huge speed up. The 12-hour test had about 6 times speed up due to these changes and executed in 2 hours instead of 12. But not only cycles can affect the performance of a program, memory allocations can affect the performance too. In this case, we were looking at the Wi-Fi HE network example, and we were tracking the memory allocations, especially the temporary allocations, which are allocations that are destroyed just after a single use or not used at all. So they are pretty much useless. One of the main sources of temporary allocations, seen the previous slide, was the Q disk drop before in Q, and it allocated a ton of standard strings. And if you look at the code, there's no allocation for string, which means it's being created temporarily by one of these functions. And by inspecting them and testing them, we can see that the only function that receives a pointer to a char or a C string are those maps and dropped packet before in queue and dropped bytes before in queue, which are transforming this C string into standard string from C++. So we have multiple different ways that we can solve this problem and reduce these allocations, but the solution we chose was to use transparent comparators, which are a feature of C++ 14 or 17, I don't remember exactly which one, but which allows the comparison between two types that can be transformed in one another without making the temporary allocation. So we reduced it in 6 million temporary allocations for that example alone. The third case I wanted to show you was the overhead caused by the operating system and drivers. In this case, we have an LTE example, but we can see clear that something really wrong going on the left side, where we have these huge flames. And by looking carefully at them, we can see they are related to files like seek, open, write. And by looking at the codes, we can see they are related to Fuse. Fuse is the user space file system for Linux, and I think other operating systems support them too. But this is caused because my test drive is an NTFS drive, which is a file system from Windows, and I was running on Linux, which didn't have a native driver yet, so it was running with an user space driver, which adds a ton of overhead and adds latency to the program itself, slowing it down. To find out which system call is slowing down the program, you can see by using ns-3 -c, a summary of the calls called by a specific program. In this case, we can see that the majority of the calls are related to files: open, close, seek, and write. And by running ns-3 with no -c, in this example, Lena radio link failure, we can see which files are being opened, seeked, written, and closed, one after the other. So we can inspect the code which accesses those files and change them to keep them open and write less frequently. By keeping those LTE trace files open, we reduced the overhead of the file manipulation by about 50%, providing a pretty good speed up. And we can see the ns-3 -c result here, that we only have the frequent calls, but not the opens, close, and seeks. We could also reduce those writes, but we risk keeping too much stuff into the memory buffer and losing it in case the process crashes. To conclude, I would say that before starting a long simulation campaign, you should build and run using sanitizers or Valgrind fix any and all memory bugs that happen in your program. And if the simulation is taking too long, try to profile it, find the source of the slowdown, the bottleneck, and try to optimize the bottleneck that you found. If you have any questions or need some help with profiling optimization, you can hit me on Zulip or send me an email. And that's about it. Thank you for watching.